You know that little bit of magic in your phone, the part that can instantly find every single picture of your cat or recognize your face to unlock itself? It feels totally seamless, almost like intuition. But here's the thing, that intuition wasn't just born overnight. Nope, it was built piece by piece from a blueprint written decades ago. So let's really get into it. How did we do that? It's a question that cuts right to the heart of what modern AI is all about. I mean, it's one thing for a computer to crunch numbers, right? But it is a whole different ballgame for it to look at a bunch of pixels and go, yep, that's a dog. Today, we're going to pull back that curtain and find the origin story.
All right, here's our roadmap. We're going to start by looking at how things used to be done, the old, really hard way. Then we'll uncover the revolutionary idea that just changed everything. We'll meet the network that actually learned to see how it went from reading single letters to whole words, and finally, we'll talk about the incredible legacy it left behind.
Okay, so our story starts by winding the clock all the way back. I'm talking before smartphones, before social media, back to the dial-up era of 1998. We are on the hunt for the source code, the very blueprint of the AI vision revolution. And we find it right here. In this paper, gradient-based learning applied to document recognition. Now I know, it doesn't exactly sound like a summer blockbuster, but this paper from Jan LeCun and his team, it was, and I'm not exaggerating, the foundational blueprint for pretty much every computer vision system we all use today. To really get why this paper was such a big deal, we have to understand what came before it. Back then, trying to teach a computer to recognize anything was just painful. It was all about pure brute force human effort. And it all came down to two totally different ways of thinking. The old way, on the left, was all about humans trying to write a set of rules for the computer. Like, imagine trying to describe the number 8. You tell the computer, okay, look for a closed loop on top of another closed loop. Simple, right? But what if the person's handwriting is sloppy, and the loops don't quite close, or the 8 is tilted? Your rules break. Instantly. The new way, the idea in this paper, was to just stop. Stop giving the computer rules, and instead just show it thousands of examples of 8s and let it figure out what an 8 looks like. This slide really just nails the problem. In that traditional model, the most important step, the feature extractor, was done completely by hand. A human had to manually program in all the intelligence. Now the second part, the classifier, that could learn, but it could only ever be as smart as the features the human gave it. That handcrafted part was the bottleneck. The whole system was stuck because of it.
And this, right here, is the turning point. The authors of the paper asked a question that was so simple but so incredibly profound, it would completely change the course of technology.
This quote is basically the entire paper in one sentence. And heuristics, by the way, that's just a fancy word for those hand-designed rules of thumb we were talking about. The argument was simple. We can build way better systems if we rely more on automatic learning and less on these fragile, handcrafted rules. It was a massive shift from programming to teaching. It was saying, stop telling the machine exactly what to do, and instead build a system that can learn all by itself. So the big takeaway, the absolute game changer, was this shift in thinking. The goal wasn't to program intelligence anymore. It was to create the conditions for intelligence to emerge, just by looking at data. It was about building a learning machine, not just a recognizing machine. Now, an idea this revolutionary needed a tool, an architecture, that was just as revolutionary to make it real. And so, enter the hero of our story, a specific type of neural network called a convolutional neural network, or CNN. And its name was LeNet-5.
The genius of this network really boils down to three key ideas. First, local receptive fields. Just think of it like the network looking at an image through thousands of tiny windows, where each little window is only trying to spot one simple thing, like a line or a curve. Second, shared weights. And this is the real secret sauce. Instead of learning a million different curve detectors, it learns one really good one, and then just slides it across the whole image. This is crazy efficient, and it means the network doesn't care if a cat's ear is in the top left or the bottom right. And finally, subsampling. This is basically the network squinting its eyes to get the gist of the image. It blurs and shrinks things down to focus on the important stuff and ignore tiny, irrelevant details.
And the machine that put all these brilliant ideas together was LeNet-5. It's a 7-layer deep network that had one single mission: to read handwritten numbers better than any machine, or maybe even any human, ever had before. So let's follow an image as it travels through this thing. An image of a 7 goes in, the first convolutional layer, C1, scans it, looking for basic stuff.
edges, corners, that kind of thing. Then, the subsampling layer, S2, kind of blurs and shrinks that map of features. Next, layer C3 combines those simple features into more complex ones, so now it might be seeing things like the intersection of two lines. S4 shrinks it down again, and by the time the data gets to the final layers, the network isn't seeing pixels anymore. It's seeing these high-level, abstract concepts that it has learned mean 7, which lets it make that final call.
So, the big question is, did it work? Well, this chart says it all. Other top-of-the-line methods at the time, they were getting error rates of 12%, maybe 5% if they were really good. LeNet-5 came in and clocked an error rate of just 0.8%. This wasn't just an improvement, it was a total demolition. It proved, without a doubt, that this new way of learning features was the future.
Okay, so a 0.8% error rate? That's a huge win. But it was in a lab, with these nicely separated digits. The real world, as we know, is a lot messier. I mean, think about a bank check. The numbers are all touching, they're overlapping, they're written sloppily. This introduces a way harder problem than just recognizing a digit. It's the challenge of segmentation.
Exactly. What does one number end and the next one begin? If you try to chop up the image before you recognize the characters, a single bad cut can make the entire string of numbers impossible to read. You just can't recover from that kind of early mistake. The system needed a way to think about where to cut and what the numbers are at the exact same time. And the solution was this really elegant idea called graph transformer networks. Think of it like this. You're not just training one specialist to recognize letters. You're training a whole team, a chopper and a reader. And they only get rewarded if they work together perfectly. The entire system gets trained from end to end to optimize for one single thing, getting the final answer right. So here's how they did it in practice. Instead of trying to make one single risky decision about where to cut the numbers apart, the system would just make tons of potential cuts. This creates this huge web or a graph of all the possible ways you could read that string of numbers. Then LeNet-5 comes in and gives a score to every single one of those little segments. Finally, the system just finds the best scoring path through that whole messy graph, and that path reveals the most likely word. It's just a brilliant way to avoid making a bad decision early on. And that brings us to the legacy of all this work, because these ideas, they didn't just stay locked away in a research paper. No, they jumped right off the page, into the real world, and eventually right into your pocket. And the impact was immediate. This wasn't some academic theory that might be useful someday. The paper itself states that by the time it was published, a commercial system using these exact ideas was already processing several million bank checks per day. This thing worked, and it worked at a massive scale, right from the very beginning. And this timeline really draws a straight line from then to now. The 1998 paper was the spark. For about a decade, computers got faster, we got more data, and these ideas got refined. Then, in 2012, a much bigger, deeper descendant of LeNet-5, a network called AlexNet, just shattered all the records at a huge image recognition competition. And that moment kicked off the deep learning explosion we are still living in. The convolutional neural networks in self-driving cars, in medical scanners, in your photo app, they are all direct descendants of LeNet-5. So, at the end of the day, we're left with this thought. A single paper with a few brilliant fundamental ideas laid the groundwork for an entire technological revolution. It literally taught machines how to see. And it just makes you wonder, right? What are the game-changing ideas being written down in papers today that are going to define the world of tomorrow? What will they teach machines to do next?